the kinds of bonds. Now, what is a covalent bond? What kind of questions can be asked? You can be asked to write a note on covalent bond, define covalent bond, factors on which it depends, or bond multiplicity, etc. So everything we are doing is like a question that can be asked for your exam. So first, bond formed by equal contribution and mutual sharing of electrons between two atoms, purpose to complete their electronic configurations. That means to have a complete octet. So many examples of covalent bonds are given here: hydrogen, ethane, water, carbon dioxide, chlorine, nitrogen, ethane, etc. Right? So for covalent bond, a scientist, Langmuir, this is also given in your NCERT, in 1919 refined the Lewis postulations by abandoning the idea of stationary cubical arrangement of octet and by introducing the term covalent bond. Now, what is this cubical arrangement? This is also part of your NCERT, children. This concept of cubical arrangement suggested that each atom can be assumed to be like a cube, where it was believed that the center of this cube occupies the kernel. So what is an atom basically? An atom is kernel plus valence electrons, isn't it? Kernel plus valence electron makes an atom. So kernel was visualized to be filling the entire center of the cube, and the corners represent the valence electrons. So as an example, if I want to express sodium by this cubical arrangement model, how would we do it? I'll just draw a cube and I assume the center is all the kernel, and I will just put one electron on one corner. Why? Because sodium configuration is 281. This is the kernel and this is the valence electron. So kernel is assumed to be filling the entire inside, and one corner because we have one valence electron. Similarly, if I wanted to express something like chlorine, what would I do? I would again draw a cube, and a cube has 8 corners suggesting octet. So I will write here, and now I'm going to put 7 electrons here. 7 corners will be occupied. Why? Because chlorine configuration is 287. This much part is the kernel and 7 is the valence electrons. I hope this is clear. This is NCERT. Okay. But Langmuir, he abandoned this idea. He did not believe in this idea, and he introduced the Lewis structures to explain a covalent bond. So this we have already discussed. Both chlorine atoms attain argon configuration, and remember, no metals can ever involve in covalent bond formation. Metals never form covalent bonds. Covalent bonds are only formed by non-metals. Okay. Number of bonds formed between two combining atoms is what we call as the bond multiplicity, also called as bond order. So bond multiplicity or bond order is number of bonds between two combining atoms in a molecule. It's a very simple concept. So single bonds, double bonds, triple bonds, any of these bonds can be existing in a molecule. You already know when two atoms share one electron pair, they're said to be joined by a single covalent bond. And let us say I ask you what is the bond multiplicity or bond order of this OH bond. I'll say bond order or bond multiplicity is 1. Similarly, what is the bond order of this OH bond? It is also 1. Bond order is only defined for one pair of atoms, that is 2 atoms, not for the entire molecule. Similarly, if I draw this ethyne molecule, the bond order or bond multiplicity here is going to be 1, here is going to be 1, and this is going to be 3. Here, you need to understand bond order is 1 for this pair of atom, for this it is 3. And for this, again, bond order is 1. So this is all that you need to understand, because I've seen children having, a problem in this part. They do not know whether bond order in a polyatomic molecule has to be for one pair or it is the overall bond order, right? There's nothing like and overall bond order. Okay, so once we know this, covalent bonds can be single, double, or triple. We cannot have bond multiplicity more than 3. So these are some examples depicted. You can just pause and check if in case you want to. So whenever an atom shares 2 pairs like this, carbon dioxide means each has bond multiplicity 2. And 2 bond multiplicity means 2 pairs of electrons have been shared. So this is the structure of carbon dioxide. You should now try making the Lewis-Strauss structures and then deciding the formal charges and then talking about bond multiplicity. Just practice doing all this. So this is ethene molecule. The bond multiplicity of ethene molecule is 1, 1 for each CH bond, and bond multiplicity for CC bond is 2. This is something very basic. You're expected to know, but please don't underestimate the importance of any question. Sometimes even a very basic question tends to confuse you. Okay, so triple bond means 3 bonds. Bond multiplicity cannot be more than 3. So we're going to move on to limitations of octet rule. This is again NCERT, very important point. This is important with respect to your school exams as well. You get to write a note on limitations of octet rule. That means the exceptions where octet rule is not applicable. So in some compounds, the number of electrons surrounding the central atom is less than 8, and they've still been found to be stable compounds. Octet rule, the Lewis-Strauss structures could not explain stability of such molecules. For example, BCl3 has only 3 pairs. Like BCl3, the structure is this. Here, octet of each chlorine is complete. Each chlorine has its octet complete, but the octet of boron is incomplete. Boron only has 6 electrons around it, but it is still a stable existing compound. Similarly, lithium chloride, lithium doesn't have its octet complete, incomplete octet. Similarly, beryllium, incomplete octet. So these examples correspond to exceptions of compounds where octet is not complete. And we also call these compounds as hypovalent compounds. Hypovalent, that means you can say less valency than 4. Okay, so now we have lithium, beryllium, boron. Why do they have incomplete octets? Because they have just 1, 2, 3 valence electrons, and that is what they can share. So mostly boron, aluminium family elements will have incomplete octet. Next very important example is of odd electron molecules. Molecules with an odd number of electrons like nitric oxide and nitrogen dioxide. The octet rule does not satisfy these molecules, and you can even be asked to, let us say, 2 important things: draw the Lewis-Strauss structure for these 2 molecules. So what problem are we going to face? If I try drawing the Lewis-Strauss structure of NO molecule, what do I observe? The total valence electrons are going to be 5 plus 6, that is 11. And remember, whenever we have odd electrons coming out as total, like even in NO2, the total electrons will come out to be 5 plus 12, 6 and 2, 12, that's 17, which means we cannot distribute them symmetrically and with pairs of electrons left, which is the norm. Let us try nitrogen and oxygen. I join them by 1 bond. Nitrogen is less electronegative, so I complete the octet of oxygen first. I get 8 electrons done, and I'm left with 3 more. 3 more if we compare this pool. So that's 8, total 11 electrons gone. Fine, but the nitrogen atom doesn't have its octet complete. It is just having 2, 3, and 5 electrons in its octet, in its outermost shell, right? So if I try now to make nitrogen contribute its electrons, let us say we rub this and let this pair be shared with nitrogen. Nitrogen still has 2, 4, 6 1, 2, 3, and 4. 7 electrons. In case I make another pair come here, now it has 9. Fine. So, what is actual bond order? The actual description of this molecule is nitrogen has 2 normal bonds, 1 half a bond, a half electron bond, odd electron bond. This bond you can see is made by 1 electron coming from these other electrons of nitrogen. The ideal Lewis-Strauss structure cannot be made in case of nitric oxide. You should also know the name nitric oxide is NO. And don't confuse it with nitric acid, which is HNO3. Okay, so these are the 5 electrons of nitrogen, and these are 1, 2, 3, 4, 5, and 6 of oxygen. How was this structure justified? This kind of sharing makes the total electrons justified, but this bond is a 3 electron 2 center bond, which is considered to be like a half bond. Remember, odd electron bonds are considered to be half bonds. Half bonds means having half the strength of a normal covalent bond. So these bonds are highly reactive. You can say the molecule having half a bond is not as stable as the one having a complete bond. So normal covalent bonds are described as, remember, 2 center 2 electron bonds. Matlab, 2 atoms, let us say this, 2 atoms sharing 2 electrons. That's a normal covalent bond. But this one is an odd electron bond where 2 centers are sharing 3 electrons and its strength is equal to half the bond. So what is the bond order of this bond? The bond order of NO bond is 2.5. Exactly in the same way, if I try drawing the structure of NO2, NO2 is also an odd electron molecule. And you can remember, you can try making the structure and you can just remember bond order of NO is 1.5 in NO2. You can remember these 2 points as questions. And if you want, you can draw the Lewis-Strauss structure of NO2 in the same way as we've drawn for NO. Now, expanded octet or exceeded octet. Some elements from 4th period of the periodic table have d orbitals also, very important, have n-1 d orbitals in case of d block and nd orbitals in case of p block elements, also available for bonding. So these can expand their octet, and we get formation of hypervalent compounds. Some molecules with exceeded octet are called hypervalent compounds. So they have more than 8 electrons in their outermost shell. So let us suppose I want to draw the Lewis-Strauss structure of PF5. I'll also explain to you how to make the Lewis-Strauss structure of PF5 by the same rules that we've studied till now. Let us start with phosphorus valence electrons 5, each fluorine 7. We have 5 fluorines, 7 and 5, 35 plus 5, 40. Right? So what do? I make the less electronegative as a central atom and connect 5 fluorines with single bonds. And this way, I complete the octet of all the surrounding fluorines. I put 6 electrons, 2 are already seen in shared form. I put 6 more, right? Now, how many total gone? Each fluorine is showing 8 electrons around it. So 8 into 5, 40. All 40 gone, nothing left for the central atom. Clear? And now let us look for formal charges. Let us say I want to find out formal charge on the central phosphorus. How do I do? Valence electrons of 5, right? What are the number of bonded electrons? Non-bonded are 0. And bonded are how many? 5 bonds means 10 electrons. So what is the formal charge on each phosphorus? 0. What is the formal charge on each fluorine? You can calculate, you'll get this also as 0. And PF5 is a neutral molecule. We can justify it using the Lewis-Strauss structure as well. 5 valence, no unshared pair, so 0, and we can draw it this way. Okay, this is a hypervalent compound. Now, similarly, if let us say I choose to draw the Lewis-Strauss structure of SF4, how do I go about? Sulfur having 6, fluorine 7 into 4, 28 plus 6 makes it 34. I make sulfur and I make 4 fluorines around it. I complete the octets of the fluorines. It will take you 30 seconds, children, to complete the structures if you're good with Lewis-Strauss structures. How many gone? 38. How? Each fluorine you can see has 8. 2, 4, 6, and this 8. Each fluorine has 8. 8 into 4, 32. We are left with 2 in the pool. So I put them here. Let us check the formal charge on sulfur. 6 minus 2 minus half of 8. 0. 6 minus 2, 4. 4 minus 4, 0. No charge and no charge on each fluorine. But what do you see around sulfur? You see 4 bonded pairs plus 1 lone pair. So that means how many electrons in all? 4 bond pairs means 8 electrons plus 2 in the form of 1 pair of electrons, that is 10. So exceeded octet, again a hypervalent compound. So similarly, I have given you examples of so many hypervalent compounds which are exceeding their octet. For your school exam, you can be asked to give an example to explain the limitations of octet rule, write a note or any one question as a multiple choice question. Similarly, we have SF6. You're going to practice all this on your own. Sulfuric acid, right? And now we come to an ionic bond. What is an ionic bond? A bond formed by, the key word here is complete transfer of one or more electrons from one atom to another. It's also called as an electrovalent bond. An ionic or electrovalent bond is electrostatic in nature. It's basically a force between oppositely charged ions, right? So sodium, in simple words, if I write sodium has 1 valence electron and fluorine has 7 valence electrons. So if 1 electron is given, lost, complete transference, 1 electron is lost by sodium to form a sodium ion and fluorine gains an electron to form a fluoride ion, then the electrostatic force of attraction between the two oppositely charged ions such that each completes its octet. Sodium was 281. So when it loses this, it is left with octet. This has 287. This gains 1, it also gets its octet. So electrostatic force of attraction between these two oppositely charged ions is what is called as an ionic or an electrovalent bond. It's formed by complete transference. Okay. This is the example I have just explained. Similarly, calcium chloride. You can be asked to draw these examples, children. And when it comes to subjective exam, a complete depiction is very important. Calcium, the configuration of calcium is 2, 8, 2. So these are the 2 valence electrons. Each chlorine, you know, is 287. So each chlorine is having 1 valence. Calcium can give 2. Each chlorine needs 1, right? So what does calcium do? It gives its 1 electron to 1 chlorine and it gives its other electron to another chlorine. And it loses 2 electrons, so forms a calcium 2 plus ion. Each chlorine gains 1 electron, so forms a 1 negative. So what does the formula become? This, and you have 2 chloride ions, which makes the formula CaCl. Or it's a bond between a calcium ion and a chloride ion. You've studied in your junior classes, just crisscross the formulas and the charges, you get the formula. calcium chloride. So ionic bond formation primarily depends on what are the factors. So this is another important question for your school exam. What are the factors that lead to formation of an ionic bond? Formation of ionic bonds primarily depends upon how easily a positive ion can be formed and how easily a negative ion can be formed, right? And what is the energy required to make a positive ion? The amount of energy that is required to remove the most loosely bound valence electrons from an isolated gaseous atom is called ionization enthalpy. The definition we studied in detail in periodic chapter, right? So we've also done large size and low ionization energy makes this process of forming easy cation formation, right? And similarly, the amount of energy that is mostly released when an electron gets added into the valence shell of an isolated gaseous atom, we get the energy released as electron gain enthalpy. So small size of the non-metallic element means high negative gain enthalpy, right? Easy anion formation. Easy anion formation. Is it good? So the third thing of importance would be, remember one point, the ionic bonds are always favored between metals and non-metals. Covalent bonds were formed between either similar atoms. Remember, covalent bonds could be formed between similar atoms like HCl, HCl, Cl, Cl, HH, NN, OO, and so on. They can also be formed between dissimilar elements. This is, I'm talking about covalent bonds, the point we've already discussed. But ionic bonds are always formed between dissimilar atoms. Please remember, ionic bonds formed between dissimilar atoms. Dissimilar atoms means one has to be a metal and another a non-metal. Okay, one has to be a metal, another has to be a non-metal. Okay, so now generally favored between the S block metals and non-metals of groups 16 and 17. Why? Because these are large in size. The metals of group 1 and 2 are the largest, and non-metals of group 16 and 17, that is halogens and oxygen family, being the smallest, so they easily make negative ions. Okay. Electron gain process may be exothermic or endothermic. Electron gain process. And ionization enthalpy is always endothermic. When is the, I'll give you an example to help you recall what you've done in your periodic chapter. The first electron added into the neutral isolated atom, this is exothermic. But when another electron adds, it becomes endothermic. First gain enthalpy is usually exo, second and higher ones are endo, and also if an electron is added to a noble gas, that is also endo. More easily between elements with low ionization enthalpies, that means large sized elements, right, which are generally group 1 and group 2, and elements with high negative value of electron gain enthalpy, generally elements of groups 16 and 17, that is small size. And these are non-metals, and these ones are metals. An ionic bond can never be formed between similar elements. Okay. Electronegativity difference has to be large between two combining atoms. Large electronegativity difference is also a reason for ionic bond formation. And the third concept comes lattice enthalpy. Higher lattice enthalpy leads to greater stability of ionic compounds. Now, what is lattice enthalpy? It's a direct measure of attraction between ions in an ionic solid. Now, just to break it down into, this is also NCERT data, lattice enthalpy of sodium chloride is minus 788 kilojoule per mole. Basically, what is the meaning of this point? Sodium converted to sodium ion and electrons. Some energy was required. Chlorine comes in the form of Cl2. So if I use half a mole of chlorine and give it an electron, this is a better depiction. This process is exothermic. Now, if I cancel off the electrons, I'm going to get sodium plus half of chlorine to give sodium ion and chloride ion, that is NaCl. Okay, so this was endo, this was exo. But these two ions, oppositely charged ions, once they are formed, they attract. They attract by electrostatic attraction. And attractions always lead to loss of energy. The energy lost is called lattice energy. And lattice energy of sodium chloride is minus 78 kilojoule per mole. That means after sodium ions and chloride ions are formed, for them to come closer and form this crystal lattice, the energy released is going to be minus 788 kilojoule per mole. Okay, so I'll summarize to make it clearer to you. So what have we talked of? We have first sodium to convert to sodium ion. Ionization energy is required. Lower the ionization energy, more easily the bond form. Chlorine takes up electron to form chloride ion. The energy released is called electron gain enthalpy. This is released, this is required. And higher this is, more negative this is, more easily a bond is formed. And when these oppositely charged ions come closer to form the sodium chloride lattice, lattice is a three-dimensional arrangement of ions, the energy released is called lattice energy. More lattice energy released is a stable bond formed. Okay, if the net outcome of these three energies is negative, only then a stable bond is formed. That means if the net outcome is energy released, a stable ionic bond will be formed. What are the properties of ionic compounds? They exist in solid state. Why? Because ionic bonds are the strongest bonds. Strongest bonds, electrostatic attractions. That is why they have high melting point and hence exist in solid state. Crystal structure, ions arranged in a regular pattern. And they're soluble in polar solvents, not soluble in non-polar solvents. Why? Because you know the solubility rule is like dissolves like. So ionic compounds are also polar. They've charge separation. They're an extreme case of polar compounds. So they will dissolve in polar solvents due to the principle of like dissolves like. They're good conductors of electricity in molten and aqueous solutions. Please understand this point very well. Children make a lot of mistakes. In this, sodium is a metal and it is a good conductor in solid state. And don't confuse these 2 points. Whereas sodium chloride is an electrolyte, a solid. It is an insulator. It does not conduct in solid state, but it is a conductor in molten or aqueous solution. Why molten or aqueous solution? In molten or aqueous solution, it splits into ions. Right? And ionic reactions are fast reactions. Why they are fast reactions? Because no bonds need to be broken. Then you put them in water, they separate into ions and they quickly interact with each other to form products. And does not exhibit isomerism, which is not very important at this stage. Now, what is the lattice energy? We've already discussed. So one point that I would like to once again point out, energy released when required number of positive and negative gaseous ions combine to form 1 mole of an ionic compound is called lattice energy. Also remember, the same amount of energy will be required to break 1 mole of lattice into its ions. Okay, that means when sodium ion and chloride ion combine to form NaCl, then minus 788 kilojoule energy is released. But when you break this into these ions, then 788 kilojoule energy will be required. So is lattice energy the energy released or required? It can be either. If you are breaking, energy is required, but if you're forming, energy is released, magnitude is the same, sign changes. Don't get confused with these questions. So this we've already talked of, and this is the formula for electrostatic forces. You can leave if you want. Okay, this is with the values, ionization enthalpy, electron gain enthalpy, and this is minus 788. If you calculate the net outcome of these three forces, it should come out to be favorably negative. Qualitative measure for stability of an ionic compound is provided by its enthalpy of formation and not simply by achieving octet. That means ionic compounds are not formed simply when an octet is completed. The energy condition should also be satisfied. And an ionic compound, a stable ionic compound will be formed when the net energy change is negative. And should lattice energy, that is the energy released when an ionic bond is formed, should it be high or low? Should be high. Should be high. High lattice energy will favor formation of an ionic bond. Okay, so I have already explained this point to you. It's written down here. It is the energy required as well as the energy released. It is discussed both ways.